Hello. Today I'd like to talk about the following question. What's linear in graphical linear algebra? Um, so I just started with the question. I don't really know in which order I'll answer it. Um, I guess, okay, let me start with what's graphical linear algebra? Actually, what's graphical algebra? Also, first things first, graphical algebra is a way of writing equations as little diagrams into the UV. So you draw a little diagram like that, and it means an equation. The equation it means, in this case, is works the following way. This thing means plus, so here we have x plus y. This means multiply by 3, so here we have 3x plus y. And this thing means equals or copies, so like those three numbers are equal. So we've got u equals v equals 3x plus y. This drawing means this equation. That's graphical algebra. Graphical linear algebra is doing graphical algebra with a specific set of little symbols. And the set of symbols we use that define graphical linear algebra are the following the following symbols. So we've got plus, this means a plus b equals c. And I only use letters to sort of explain the drawing thing in terms of the normal equation things. But as you can imagine, I could choose any label, any letter, and it would still be valid. Okay, this one is a equals 0. This one is equality. That's a equals b equals c. This one is an interesting one that I could talk about for a while, which essentially says a equals whatever. So essentially, this is an equation that is true of any a. So it's true for a equals 0, or for a equals 42. It's just always true. And finally, for some k, for some number k, this is k a equals b. So that's multiplication by k, and k is some number here. So above I used 3, I could use any number. This is the basic building blocks of graphical linear algebra. And we plug these things together and we get equations in 2D. And we get, a pretty large set of equations. We can write a lot of things in this language. But I guess to answer my original question, there's something about those things that is linear, whatever linear means. So let me explain what that means. What does linear mean? Linear means straight things, right? Straight lines, straight planes. It's kind of the opposite of curved. So if I draw, a 2D plane, right? If I imagine a set of things in the 2D plane, a set of points. Here's a set of points. It's got 3 points. Here's another set of points. It's got plenty of points, and it's very curved. Here's a set of points. That one is a line. The set of points could be the whole space. The set of points could be, half the space like this. There's plenty of sets of points I can find. But some of them have this straightness to them. And like there's a particular like formal definition of what I mean here by straight, but intuitively you can see that, you know, this is clearly not straight and this is clearly straight. And it is the case that the relationships we can wow, I've made a leap here that I don't know how clear that leap is between these things, or these things built from that, and sets of points. So I guess I'm going to first do that. Okay, so imagine I have a drawing, for example, this one. Imagine I have a drawing made, an equation made from these building blocks. Why can I see this as a set of points, set of values? Well, this tells me a particular relationship between x, y, u, and v. In fact, this is the relationship. So certain choices of x and y and u and v validate this. For example, why is my thing is not working as I'm used to? If I choose, I could choose, you know, x equals 1, y equals 0, u equals 3, v equals 4. This is a point. This is, I guess, what I call a point, a choice of values. And this choice of values does not validate this equation, among other things, because u is not equal to v. This one, however, does, because we do have that u equals v, and they're both equal to 3 times x plus y. So some points validate this equation, some don't. And so if I kind of draw, here I only have 2D, but like, if my equation was, I don't know, like x, I mean, this is an equation, I guess, to be, or I could, you know, this is some equation between x and y. This is, you know, some drawing, and it tells me that maybe this point is in it, and this point is not, and then this point is, and then things like that. So this describes a set of points. And by linear, we mean that whatever this describes has a straightness to it. In fact, if we look at what this means, this means, you know, we have x here, x, we have 3x. So y is, the equation, it's like y is 3x plus x, which is 4x. That's 4x. It's a convoluted way of writing 4x. So I could have written like this, right? And y equals 4x is a line of slope 4. So that's more like a line like that. Definitely straight. And whatever that is straight in a higher dimension, so it might not be a line, it could be some plane, also hyperplane. And so roughly, waving hands, this is what we mean by linear. There's a straightness to all of things. What does this straightness look like formally? What does it mean? Well, it means two things. And let me take here an arbitrary equation now with maybe 4 points. This works with any number of things. You know, x, y, u, v. This this tells me, given 4 points, whether or not they're valid. And there's a very important property. There's two very important properties. The first one is that if I have a set of points that are valid, so for example x, y, u, v, and then I multiply all of them by some number, okay, suddenly I'm describing some other set, right? So suddenly here, those x, y, u, v are the things that validate the equation, but now the 4 points described by this new diagram are slightly different. They're like sort of scaled up version, right? It says that if I had this point in E, then suddenly this thing described, let's call this E prime. If this is E prime, then this is sort of scaled by K, right? Multiply all the things by K. So this one is in E prime. Well, one rule of linearity is that this, in fact, is included in E. It's even like equal to E. So if I take any point that validates the equation and scale it, then it still validates the equation. Which is very strong. That's a very strong statement. And it's definitely not true of all equations. Here's an equation, x equals 1. Here's an equation that doesn't have that. So if x equals 1, 3x is not equal to 1. So this inclusion is not true of all equations at all, but it's true of all equations made from this. It's true of all linear equations. And we can see it, that it works for all the basic elements, right? So for example, if I have, this is x plus y equals z in the middle here, and so the overall equation here will be this is slightly tricky. Well known x, y, z. This is, x plus y equals z, and then a equals kx, b equals ky, c equals kz. So, assuming that k is non-zero, this is the same as a over k plus b over k equals c over k, right? This bit is the same as this. But we know that this, we can just multiply this equation by k, right? This is the same. This is for a non-zero k, this is true exactly when a plus b equals c. So this relationship between a, b, and c is the same as this one. So scaling up the plus little equation gives you the same thing, which is what we want here. We only need the inclusion, but it works in general. And the zero case is also very interesting, the case when k equals 0, because what it means is that if I multiply all the things by 0, it's it's actually not scaling, it's collapsing everything into 0, right? If I pick k equals 0, notice that 0 multiplying by 0, what is this? That's like 0a equals b. This equation 0a equals b is kind of just the equation, 0 equals b. It's the same thing. And the way you write this, another way of writing this is, b equals 0. We know how to write that. And a is whatever. Whatever a doesn't matter. This is the same equation. 0 equals b and 0a equals b is the same thing. So multiplying by 0 is a particular thing we can draw like that. So if we write this in the case of k equals 0, for k equals 0, we get, all the multiplying by 0 is like all the things are 0. So take x, y, u, v in E and multiply them all by 0, and they need to be in E. So in other words, if we set all of them to 0, we need them to be in E. Which, that's again a strong statement, because it means that 0 is always validates all our equations. And, well, turns out it does. Well, obviously this one, if a equals b equals c equals 0, then they're all equal, okay. This is true for anything, it's true for 0. Well, k times 0 equals 0. Yeah, so 0 is always a solution. Oh, this one as well. 0 plus 0 is 0. Yeah, 0 is always a solution of all these equations. But that's obviously not true of all the equations we can think about. Again, the equation x equals 1. Well, 0 is definitely not a solution. 0 is not equal to 1. So here's another thing that linearity tells us, is that we can always scale the thing, right? Well, or rather, the set is unchanged by scaling, and in particular it contains 0. So like a set like this definitely doesn't work. It needs to contain 0. So maybe a set like this, well, no, because we need to be able to scale it. So this point is in it, and the rule here tells me that also therefore this point must be in it. So if I wanted this to be a linear set, then I need to include also, all the scaling versions of this one and also of this one. So that scales that way, and also of this one. So that scales that way. So actually the set would be more like this whole cone. That, if you take this whole cone, that is closed under scaling. It's still not quite linear, or what we mean by linear. This is so far this description defines coney things like that can sort of stretch as much as we can. But there's one more rule for linear, which is, I guess, slightly less intuitive, possibly. Okay, so this is one rule for linear, and the other is that if I have some points in E, you have two sets of points that are in E. For example, if I have, for this example, if I have, x equals 1, y equals 4, and I also have x equals 3, y equals 12. If I start from two sets, then it is the case that the sum of the points is also in the thing. So I sum the points, right? So if I have x and x prime and y prime, etc., then I will have here, that will be x plus x prime, right? That's x prime. And the rule is that those things are also in E. Let me know. Okay, this is what it is. That's the second rule of linearity. That whenever I have some 2 points in my thing, then their sum is also in the thing. So for example, if we took this cone thing, well, let me change color maybe. If I have a point here and a point here, then their sum will be this point here, and must be in the set, which it is right now. That's cool. But also this one, plus, so that kind of sums to 0. Let me find a better example. Maybe this one. Oops. Maybe this point here and this point here, right? And they sum to it's like something like, okay, they sum to this point here. So that means that this cone thing is not linear yet, because it doesn't contain all the sums. It would need to contain this thing and all its scaling up, and in fact it would need to contain, in this case, like all of the points around here, and then all of the points, and you need to contain everything. If you add the sums into that, you need you get everything. What about this case? Do we have the sums? So the claim is that these are two sets of points that are clearly in here. What about their sum? So that's x equals 4, y equals 16. Oh yeah, that also validates this. Cool. It's closed under sum. And in fact, all of these are, which is not too hard to verify. For example, this one, we can write it. Is it the case that kk, so that's like x, let me ABCD, I like ABCDs, ABCD. So this is the equation Ka equals C, Kb equals D. Is it the case that it's included in the equation, this one, right? So that's Ka plus B equals C plus D, right? Again, A, B, C, D are here. But this one is the same as Ka plus Kb, right? If C is Ka and D is Kb, then yeah, that's clearly the case. So if this is true, then this is true. Good. This is an example of this rule being true. This rule is definitely true for all of that. And again, this is not true for all the things we can think about. If we take x equals 1, right? If I have 2 points that validate this, so I have x equals 1, x prime equals 1, then x plus x prime does not validate the equation. Okay. So this is what we mean by linear, and I don't know if it might not be immediately apparent why. I don't really know why, like exactly. It's hard. I don't know how to explain why this is useful as a concept. It so happened that the linear things are very well behaved. They're convenient. Not only do they pop up all the time in lots of sort of concrete cases, but they're very convenient. You can think about them and prove and like solve them pretty easily. Oh, the last thing I want to say. So this is what it means to be linear. This is a special case. So these two things are what it means to be linear. And not only I said so far that the equations written from this are linear, but in fact, it goes the other way around. All the linear equations can be written from these. So these describe exactly all of the linear things, which is why we call that like graphical linear algebra. Is this we can do linear algebra, which is the algebra of the linear things, using just that. Pick any linear equation and bam, we can write it like this. Which is why it's so cool. Okay, so this was, why do we call it linear? And I don't feel like I've done a good job of explaining why this is an important notion, but I feel like I've got a decent job of explaining what the notion is. So I'll end up here. Thank you for watching.